Hi everyone, now we are at sequences and series, lecture number 8. So in today's class we are going to discuss a few problems related to theorem number 1, geometric series. Okay, here the problem number 1. First let me recall what is the theorem statement. Okay, so the geometric series theorem says that series A r power n minus 1, n is running from 1 to infinity. This series is converges to A by 1 minus r provided if modulus of r is less than 1. And the series is diverges or not converges, whatever, diverges if modulus of r is more than or equals to 1. This is what we discussed in the last class, which is theorem number 1. So based on this theorem, let us do few problems. So here you observe n is running from 1 to infinity. You can write this theorem, this expression like this also. Like so instead of writing like this, you can write series index. You can change from 0 to infinity also, no problem. If n is running from 0, it is a r raised n. Previously it is n minus 1. If I substitute n is equal to 1, what I will get? First term will be a, isn't it? First term is a, second term is ar square, plus third term is ar only ar, right? Ar square plus up to so on. Same terms only will get here. What is the first term? N is 0. First term is a, second term is ar, third term is ar square, like this up to so on. Just I am changing index n is 0 to infinity, then here r power n. Okay, observe all these things, but result is same. It is converges to a by 1 minus r. What is a? First term of the geometric series, and r is the geometric ratio, common geometric ratio. Yeah, let us attack this problem. What is given? So let the given series is, assume it is an, series an, which is series n is running from 1 to infinity, 1 upon 2 into 1 upon 3 raised n minus 1. Now look at, you compare this series with geometric series, this one. See, n is running from 1 to infinity, n is running from 1 to infinity. Instead of a, you are having 1 by 2, and instead of r, you are having 1 by 3. If you compare with this, or if you are confusing, just write the terms. Substitute n is 1. What will you get? 1 by 2. Okay. Next, substitute n is equal to, next plus n is equal to 2, you substitute 1 by 2 into 1 third. Okay, this is n is 2. Next, n is equal to 3, substitute 1 by 2 into 1 third power 2. Okay, 1 third power 2 plus 1 by 2 into 1 third power 3. 1 third power 3 plus up to so on. So these are the terms of the series. So therefore, in this, what is a now? Clearly, so therefore a is equals to first term, right, which is 1 by 2. Is it geometric series? How to decide? It has to be common ratio, right? What is r now? 1 by 2 into 1 by 3 divided by 1 by 2. So you are getting 1 by 3. Similarly, you take third term divided by second term. Again 1 by 2, 1 by 2 cancel out, 1 by 3, 1 by 3, 1 time cancel out, again 1 by 3. So therefore, it is having common ratio r. Therefore, it is a geometric series. First, you have to conclude, does it a geometric series or not? If it is a geometric series, then only we can apply this theorem. Okay, clearly it is a geometric series, and a is 1 by 2, r is 1 by 3. So therefore, directly, so therefore, by geometric series theorem, so therefore, by theorem number 1, the given series, the given geometric series, okay, because it is geometric series, the given geometric series converges to which number? A upon 1 minus r, a upon 1 minus r, which is nothing but, what is a? A is 1 by 2 upon 1 minus r, common ratio is 1 third. So overall 1 by 2 into 3 by 2, because 1 minus 1 by 3 is 2 by 3, reciprocal 3 by 2, so 3 by 4 is the answer. Therefore the given series converges to 3 by 4. So therefore final conclusion, so therefore summation n is running from 1 to infinity, okay, 1 upon 2 1 third raise n minus 1 is how much? 3 by 4. So the given series converges to 3 by 4. Okay, next one, continuation, problem number 5. Find the sum of the series or find the converging point of the series. Again, let us decide first whether it is a geometric series or not. If it is a geometric series, then only you can apply. Okay, so first let us call the given series is let us call it as Bn. So series 2/3 into minus 1 by 2 whole raise n. Look at here, now n is running from 0 here. Okay, n is running from 0. So don't get confused with the index n is 0 or n is 1, because the theorem n is equal to 1 to infinity I have written, and it is a into r to the power of n minus 1 I have written, but it is not in this correct format. So if you want to express this one in that format, or simply look at the previous problem. In this previous problem, it is exactly in the geometric series format. Look at a 1 by 2 and r to the power of n minus 1, and n is running from 1 to infinity. Therefore this is a, this is r directly. A is 1 by 2, r is 1 by 3. Therefore in the formula substitute a is 1 by 2, r is 1 by 3. That's it. A upon 1 minus 1 direct answer without applying all these things. Okay. For this problem, it is not exactly in that format, but you can express this one in that format also, or directly you can write what are the terms now. If n is equal to 0, it is 2/3 plus. If n is equal to 1, it is 2/3 and minus 1 by 2 plus n is equal to, it is 2/3 and minus 1 by 2 power 2. And one more thing you have to observe here, before applying this geometric series, compulsory, see what does it mean, your r is lying in the interval minus 1 to plus 1, right? Minus 1 to plus 1, r must be in this interval only, then only the series converges. Here what is r? R is 1 by 3, compulsory you write this is less than 1. Okay, if it is more than 1, this one does not converges. Compulsory r should lies in this interval only. So if you want, you can write this one very clearly. So this will be so since 0, or simply instead of writing 0, let me write minus 1 less than 1 by 3 less than 1. So since the r value lying in this interval, therefore the series is converges. Okay, converges to a by 1 minus r. That one compulsory you have to check. So for this problem, yeah, let me write the terms, then I will verify. So 2/3 minus 1 second power 3 plus up to so on. Okay, now in this first term is, what is the first term? A is 2/3, a is 2/3, and what is r? Are you getting the same ratio, minus 1 by 2 upon 2/3. So 2/3 is out, you will get minus 1 by 2. Is it same for all? Look at, you can look at a3 by a2. What are you getting again? 2/3 cancel out, minus 1 by 2 one time cancel out, minus 1 by 2. Again a4 divided by a3. Again same here. You have to get same ratio, then only it is in geometric series, in the geometric series format. Okay, and since r is lying in the interval minus 1 to plus 1, so condition is satisfying. So therefore by geometric series theorem, or by theorem number 1, you write the theorem statement in exam. Compulsory you write the theorem statement. By theorem number 1, the given geometric series, converges to a upon 1 minus r. Okay, a upon 1 minus r, which is nothing but what is a? A is 2/3 divided by 1 minus of minus 1 second. So this will be 2/3 into 3 by 2 set plus 3 by 2, so 2 by 3. 2 by 3 into 2 by 3, which is 4 by 3. 4 by 9, sorry. 4 by 9. So therefore, the given series, what is the conclusion? So series 2/3 and minus 1 second raise n is converges to 4 by 9. That's it. So this is a conclusion. Or one more way also I can do this. See, this is a second way, second method. Let me proceed here. So second method. Okay, how to do the same problem. First, you try to express this problem in standard format, like series n is running from 0 to infinity. It is running from 0 to infinity. 2/3 into minus 1 second raised n. This can be expressed as series. Instead of writing n is 0, let us write n is equal to 1 to infinity. Okay, so 2 by 3, right? 2 by 3 minus 1 whole minus 1 by 2 whole to the power of, I am writing n minus 1. That's it, nothing else. So indirectly, what I am writing here, if I substitute n is 1 here, what will get? First term is 2/3. Look at here, what is the first term? First term is 2/3. Next, second term here, n is equal to 2 you substitute. What will get? 2 by 3 into minus 1 by 2 whole power 1. Same, look at 2 by 3 into minus 1 by 2 whole power n. Like that. So we are getting same terms. If you are increasing 1 here, here you have to decrease 1 in the power. Okay, 1 2. So now it is in the standard format. So therefore, so directly I can write a is 2 by 3, and what is r is minus 1 by 2. That's it. So you apply the formula a by 1 minus r in this, substituting this, and you will get the answer. That will is 4 by 9. So directly like this you can do it if you express in a standard format. Or if you are confusing with n is 0 to infinity, or if you are confusing like this index n is 0 to infinity or n is equal to 1 to infinity, don't get confused. First you write the terms like this. Look at the problem. N is equal to 0, write on first term. N is equal to 1, write on second term. N is equal to 2, write on third term. And observe, is this geometric series or not. Okay, if it is geometric series, then you can proceed, find out what is a and what is r, and if it is satisfying the condition, then the series converges. If it does not satisfy this condition, this series diverges. Okay, next, continuation problem number 6. Find the sum of the series or find the converging point of this series. So first one, so series n is running from 1 to infinity. Now series n runs from 1 to infinity. What is that? 3 raised n, right? Now 3 raised n, 3 plus 3 square, that means n is equal to 1, 3, n is equal to 2, 3 square, plus n is equal to 3, 3 power 3, plus n is equal to 4, 3 power 4, plus up to so on. Is it geometric series? Yeah, it's absolutely geometric series. A is equal to 3, first term is 3, and what is common ratio? 3 square by 3, I am getting 3. And look at 3 power 3 by 3 square, again 3. 3 power 4 by 3 cube, again 3. It should be always true. Then only it is in geometric series. Yeah, it is perfectly geometric series. But here what you are having is, but r is equal to 3, r is equal to 3, it does not lies in the interval minus 1 to plus 1, right? Minus 1 to plus 1. It has to be between minus 1 to plus 1, but r is equal to 3. So therefore, the given geometric series, it is geometric series only, but condition not satisfied. The given geometric series, modulus of r should be less than 1, right? But it is not less than 1. So it is, so if r, that means what? R, simply I can write modulus of r is more than 1. So modulus of r is more than or equals to 1. It is satisfying this condition. This condition is satisfying. So therefore the given geometric series, does not converges. That means it is diverges. So it is diverges to simply, by observation I can say that it is infinity. I no need to apply the geometric series theorem. Directly you can look at here, 3 plus 3 square, 9, 9 plus 27 plus 81 plus up to so on. If you add all these terms, what you will get? You will get infinity. So therefore it is plus infinity. So therefore it is not finite number. So therefore directly without using any theorem, therefore the series is diverges. That's it. The geometric series theorem is not required now. We can conclude in so many ways. Okay, the thing is you have to be, the subject should be in your grip. Yeah, second problem, series n runs from 0 to infinity 1 upon 2, just 1 upon 2. Now what is this? What is the first term? Look at here, power n is not there, just 1 by 2 only. That means it is constant series. So first term is 1 by 2, second term is again 1 by 2, third term is again 1 by 2, fourth term is again 1 by 2. So each and every term is 1 by 2 only because it is constant series. Now what do we get? So by observation clearly, what I can say here, so 1 by 2, 1 by 2, 1 by 2, 1, we keep an add all these things. What do you get? 1 by 2 plus 1 by 2, 1, 1 plus half, 1 and half, right? 1 and half plus half, 2, 2 plus half, 2 and half, keep on increasing. Therefore, it is possibly infinity. Therefore, it is diverges. The series diverges. You may get doubt here. Yes, the series diverges. And you may get doubt here. The doubt is, it is geometric series, right? Look at, yeah, let me write here. So the given series, particularly this series, in this series, what is A? A is equal to 1 by 2, first term. What is R? R is equal to 1. It is true. So therefore, there is geometric series. And R is equal to 1 is not satisfying this condition, right? R should be minus 1 to plus 1. Then only the series converges. Otherwise, the series is diverges. So therefore, the series is diverges. By using geometric series also, you can conclude. Okay, R is equal to 1, not satisfying this condition. It is satisfying which condition? Modulus of R is more than or equals to 1. Second condition is satisfying. Therefore, the series is diverges by geometric series. Okay, next one. Problem number 7, continuation. Express the repeating decimal 4.252525, that means 4.25 whole bar, 25 is repeating, as a rational number. And these problems you have seen in 10th class, like let's say x is equal to this number, and next 100 into x is equal to 425.2525, then subtract both, you will get that. That is a different. But I want to attack the same problem by using the concept of series. Okay, by the concept of series I want to apply. Look at how 525, so 4.25 bar is nothing but 4.25, 25, 25, 25 and up to so on here. 2 to the digits are repeating. And this I can write as 4 plus 0.25. Can I write? Plus. So these two are next 0.0025. Okay. Next up to this is over. Next to 4 zeros plus 0.000025. If you add all these things, you will get the given number 4.252525 like this. But this I can write as 4 plus. This one I can write as 25 upon 100 is nothing but 0.25, right? And this is 25 upon how many points after decimal? 4 points. That means 100 into 100 or 100 square, you write. Okay. Next 25 upon after decimal how many points? 1, 2, 3, 4, 5, 6. So 100 into 100 into 100 or simply 100 power 3 plus up to so on. Okay. Next 4 plus 25 by 100 I am taking common from the rest of the terms. So what do you get? 1 plus 1 by 100. Here 25 by 100 is out, and here 1 by 100 square. Okay, plus up to so on. You observe these terms here. This is a geometric series with a is equal to 1. First term is 1, and what is common ratio? R is 1 by 100. Does it? Remember, it should be infinite series, infinite numbers. Okay. Common ratio is 100, therefore it's a perfectly geometric series. And not only that, and R is equal to 100. Okay, the common ratio R is equal to 1 by 100 is lying in the interval minus 1 to plus 1. Perfectly, the condition is satisfying. So therefore, this will be 4 plus 25 by 100. 25 by 100. So therefore, this is converges to A by 1 minus R. Is nothing but 4 plus 25 by 100. Okay, now what is A? A is 1 minus 1 upon 1 minus R, 1 by 100. This is nothing but 4 plus 4 plus oh, 25 by 100, 25 by 100, and this is 99 by 100, so 100 by 99, 100 by 99. If you reciprocal this, and here 100 cancel out. Okay, now what will remains? 4 plus, so this will be 4 plus 25 by 99. Okay, now take LCM and simplify. 4 9 is 36, 6 and 3, and 4 is 36 plus 3, 39, 396. Okay, and plus 25 by how much? 99. So final answer is 306 means it is 421, 421 by 99. So this is a rational number, 421 by 99. So this is the final answer. So therefore 4.252525 is nothing but simply 429 by 99. So you can conclude like this. So therefore final comment is 4.2525 bar is nothing but just 421 by 99. So this is the final answer. So they are expressing the repeating decimal as a rational number. What is my rational number? A number which is in the form of p by q, where q not equal to 0. That is called rational number. So p by q format will be expressed in this, and p is 421 and q is 99. Okay. So this is one of the application of geometric series. Okay. So next one, special series, that is a telescoping series. So a series AN is said to be telescoping series if the terms of Sn, what is Sn? Nth partial sum, other than first and last cancel out in pairs. So in the nth partial sum, other than first and last, every terms cancel in pairs. Such kind of series is said to be telescoping series. Example, this one. Series n is equal to 1 to infinity, 1 upon n into n plus 1. Okay, let me elaborate this. So now, so let the given series, we call it as some an is series 1 upon n into n plus 1. Okay, so therefore what is nth term of the series? An is 1 upon n into n plus 1. This is nth term of the series. Okay, now what I want, a series an is said to be telescopic series if the terms of Sn, nth part of sum. So therefore I need to construct what is Sn. What is Sn? A1, sum of first n terms of the series, right? A2 plus up to so on plus an. This is sum of first n terms of the series. Now what is A1 now? Substitute here n is 1, you will get 1 by 1 into 2. The second term, substitute 2, 1 by 2 into 3 you will get. Substitute 3, 1 by n is equal to 3, you substitute 3 into 4 you will get. Okay, plus up to so on. What will you get? Substitute, so before term, let me write this is an minus 1 plus an. Let me write one term extra. But first, sum of first n terms only. What is n minus 1? 1 upon n minus 1 into 1 upon n minus 1 into n. Plus, what is an? 1 upon n into n plus 1. Okay. Yeah, Sn is written. Next, if the terms of Sn other than first and last, other than first term and last term, cancel out in pairs other than first and last. So this can be written as already this kind of terms you have seen in sequences, right? So 1 upon 2 minus 1 upon 3, I can write this one. Second term, first term 1 by 2, so I can write 1 by 2 as 1 minus half. You simplify, you will get 1 by 2. Second term 1 by 2 into 3, 1 by 2 into 3, you can write 1 by 2 minus 1 by 3. If you take LCM, again you will get back same. What is LCM? LCM is 6, right? So LCM is 6. Look at this one. I am simplifying this, and 2 3s are, so 3 minus 3 2s are is nothing but 1 by 6. Look at, you are getting 1 by 6. Second term. Similarly, third term I can write this one as plus 1/3 minus 1/4, like this. Okay. So plus to so on plus n minus 1th term. So 1 upon n minus 1 minus 1 upon n I can write, right? And plus 1 upon n minus 1 upon n plus 1 I can write. You simplify this again, you will get back the same terms. And now, except first and last terms, what is the first term in this expression? 1 is the first term. What is the last term? 1 by n plus 1. Except first and last, every term will cancel. Let us verify. Minus 1 by 2 plus 1 by 2. Minus 1 by 3 plus 1 by 3. Minus 1 by 4 next plus 1 by 4. Like that. So, minus 1 by n plus 1 by n. Here 1 by n minus 1. This also will cancel with the next bracket minus 1 by n minus 1. Likewise, each and every term will be cancelled out. So, here what is left? First term is 1 and last term is 1 upon n plus 1. So, this is left. So, this is the last one and this is the first one. That's what here the definition. A series AN is said to be telescoping series in the terms of Sn, that means nth partial sum, other than first and last cancel out in pairs. All the terms are cancelled out other than first and last. Such kind of series is said to be telescoping. Therefore, this series is telescoping series. One special series, that's it. Okay. And related to that, problem number 8, continuation. Find the sum of this series. So it is a special kind of series. This is a telescoping series. Before that, you don't worry about what kind of series it is. In general, how to find the sum of a series? First, we need to construct nth partial sums, right? So then proceed. Let Sn be a sequence of nth partial sum. Okay, be a nth partial sum. The approach in general method, nth partial sum. Nth partial sum. Therefore, what is Sn now? Sum of first n terms. Let's say a1 plus a2 plus up to so on an, and is nothing but 1 upon 1 into 2 plus 1 upon 2 into 3 plus 1 upon 3 into 4. Okay, plus up to so on plus 1 upon n into n plus 1. N plus 1. We simplify this. Already I did just now. Direct I'm writing. So 1 minus 1 by n plus 1 I will get. So this is Sn. Okay. Now at what number this sequence converges, let us find out. So limit n tends to infinity. What is Sn? So limit n tends to infinity. What is Sn? 1 minus 1 upon n plus 1. So sequence of nth partial sum. So what is this answer? It will be 1 minus 1 by infinity, that is 1. So therefore conclusion is, therefore sequence of nth partial sum is converging to 1. So therefore the series AN, which is, what is that? Series 1 upon n into n plus 1. So this is also converges to 1. That's it. Or simply you can write this one as, or simply therefore series n is running from 1 to infinity, 1 upon n into n plus 1 is equals to how much? 1. So sum of all the terms, that means this 1 into 1 by 2, 1 upon 1 into 2, 1 upon 2 into 3, 1 upon 3 into 4, up to so on, to take infinitely many terms is equals to, therefore the sum of all these infinitely many terms will be 1. Okay. Next one. Theorem number 2, continuation. Theorem number 1 we did in the last class, that is geometric series theorem. Now theorem number 2. If the series AN converges, listen carefully, the series AN converges, then nth term go to 0. Limit n tends to infinity, AN will be 0. Don't think about converse. If limit n tends to infinity, AN is equal to 0, it doesn't mean that sequence converges. I am not saying that. If sequence converges, then only nth term go to 0. It is not if and only if statement. Okay. First, what is given? Sequence should converge. Then what I can comment? I can comment as limit n tends to infinity, AN should be 0. Look at the proof, you will understand clearly. Proof. So given that, listen carefully, given that series AN converges, series AN converges, okay, we have to prove that. So then we have to prove that AN will be 0. This we have to prove. Okay. So what is given? Series AN is converges. So therefore, since series AN is converges, series AN is converges, so therefore series AN is equal to some L, let's say, because it is convergence, right, where L is finite number. Sum of all the numbers is L. Okay, so now, so therefore what I can say, once the series converges, therefore its nth partial sum, sequence of nth partial sum, sorry, not nth partial sum, because that is sequence, right, its sequence of nth partial sum, sequence of nth partial sum Sn, sequence Sn, this one is also converges to same number L. Why? Because series is converges to L, therefore its sequence of nth partial converges to L. That means what? That is limit n tends to infinity, Sn is equal to L, right? Its meaning, because sequence converging to L means what? Limit n tends to infinity, Sn is L. See, series An is L, you don't write, therefore limit n tends to infinity, An is L. Okay, so from this you don't write limit n tends to infinity, An is equal to 8, An is equal to 8. This is wrong, absolutely wrong. This is wrong. Okay, if series converges to L, then its sequence of nth partial sum is converges to L. That means limit n tends to infinity, Sn will be L. Okay, so so from this, so Sn is a sequence, so therefore it is converges to some number L. So therefore it is a converging sequence now, right? Sn is a converging sequence. So what can you see at Sn minus 1, Sn minus 1 is a subsequence of sequence Sn. So once sequence Sn converges to L, therefore I can say that the subsequence Sn minus 1 is also converges to same limit L. Okay, that implies limit n tends to infinity, Sn minus 1 will be how much? L. So now assume this is number 2. So now the look at the modifications here. Sn minus 1 I want to do. Okay, now what is this? Sn means a1 plus a2 plus up to so on plus an, sum of first n terms, right? Minus Sn minus 1 means sum of first n minus 1 terms, a1 plus a2 plus up to so on plus an minus 1. You look at in this first bracket, what is the before term of an? It should be, what is the before term of an? So plus, before term is an minus 1, right? An minus 1. After that next one is an. Okay, now in this, look at a1 minus a1 cancel out, plus a2 minus a2, and plus an minus 1 minus an minus 1. What is left? Only an is remaining. Therefore here this is just an. Okay, so Sn minus Sn minus 1 is an. Now apply limit both sides. Apply limit both sides. Why I need to apply limit both sides? Because I need to prove, look at this one, I need to prove limit n tends to infinity, an is equal to 0. An already I got, look at the RHS side an I got. The next what I want, limit n tends to infinity I want extra. So therefore that's why I'm applying limit n tends to infinity both sides. Then what will get? So therefore limit n tends to infinity, okay, Sn minus 1 is equals to limit n tends to infinity an. So therefore what will get? What is limit n tends to Sn value? L, right? Look at from 1. And next limit n tends to Sn minus 1 value, again this is L. L minus L is equal to limit n tends to infinity an. Since by using 1 and 2, since by using the equations 1 and 2, from 1 and 2 we have written this step. Okay, so therefore overall, so therefore final comment is limit n tends to infinity an is 0. That's it. Over. So from now onwards, if you are having a convergence series, then conclusion is limit n tends to infinity, this an will be 0. That is a conclusion. Okay, so based on this theorem, let's have the examples. Okay, yeah, look at this first one. So this I can write series n is running from 1 to infinity, 1 by 2 whole to the power of n. Okay, expand the terms, what will you get? 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus up to so on. Therefore, now what is a? A is equals to 1 by 2, and what is r? R is equal to 1 by 2. Okay, and since r is lying in the interval minus 1 to plus 1, it is satisfying the condition, or common ratio should be minus 1 to plus 1 because r is off. So therefore the given series converges to a by 1 minus r by geometric series theorem. So what is a now? A is 1 by 2, 1 minus 1 by 2. So answer is 1. Therefore the given series, this one is converges to how much? 1. So therefore this is convergent series, right? Now look at the previous theorem number 2. We are having a convergent series. Therefore limit n tends to infinity, limit n tends to infinity. What is a n now here? So limit n tends to infinity. Okay, now what is a n? 1 by 2 to the power of n is nothing but 1 by 2 to the power of infinity is nothing but 1 by infinity is nothing but 0. Look at verified. So every convergent series should have the nth term go to 0. Similarly here, this telescoping series just now we computed. What is the sum? Again the sum is 1. Okay, and what is an here? An is 1 upon n into n plus 1. Now apply limit. So now apply limit here. So limit n tends to infinity, n tends to infinity, an. So limit n tends to infinity, 1 upon n into n plus 1. Instead of n, we write infinity. So 1 by infinity, this is 0. That's it. Look at, right? So if you're having a convergent series, this is convergent series, therefore nth term is going to 0. So this is convergent series, therefore nth term going to 0. But what about converse? Converse of the above theorem number 2, this theorem number 2 is need not be true. That means, what is the theorem statement? So if limit n tends to an is 0, then series need not be converges. This is converse of the theorem statement. Original statement is what? If series is converges, then I can say that nth term go to 0, right? This limit nth term go to 0 means what? Limit n tends to an value 0. But here, what is the converse? Reverse of that. So if limit n tends to infinity an is 0, then the series may not be converge or need not be converge. Example, look at this example. Limit n, series n is running from 1 to infinity, ln n by n plus 1. Now look at, so first I want to calculate limit n tends to an value how much. Okay, so let us take, so this is best example to say that the converse need not be true. So let series an is series natural logarithm function of n upon n plus 1. Okay, where n is running from 1 to infinity. So therefore limit n tends to infinity, what is an nth term? So limit n tends to infinity, ln of n by n plus 1, n by n plus 1. So yeah, what is this? So which is limit n tends to infinity. So natural logarithm function of numerator n into 1, that means I am taking n common, denominator n into 1 plus 1 by n. Okay, so overall this n cancel out. Then apply the limit, what will you get? So ln of 1 by 1 plus 0. What is ln 1? 0. Look at, I got limit n tends to an value 0. So therefore final conclusion is, so therefore I can write here, so therefore limit n tends to infinity, an value 0 I got. Okay, now let us verify its status, convergence status. Let me verify the convergence status of the series. Yeah. So given series an, which is series ln n upon n plus 1. So this is given series. N is running from 1 to infinity. Okay. N is running from 1 to infinity. Okay. Is nothing is given means it is n is running from 1 to infinity you have to take. Okay. If nothing is given. Limits nothing is given. Yeah. So to say the convergence status of this series, first we need to construct the nth partial sum of the nth partial sum of the series. What is that? So let Sn be the sequence of nth partial sum. Sn be the sequence of nth partial sum. Nth partial sum. Okay. If the sequence of nth partial sum converges, then the series converges, right? So therefore Sn plus an, sum of first n terms, right? And now what is a1? So therefore here I can write what is an now. An is ln of n by n plus 1. This is nth term of the series n by n plus 1. Yeah. What is a1? a1 is substitute n is 1 here, 1 by 2, right? So ln 1 by 2. ln 1 by 2 plus what is a2? ln 2 by 3. Okay. Next a3 substitute n is 3. ln 3 by 4. ln 3 by 4. So plus up to so on. What is a n minus 1? Substitute instead of n minus 1. So ln n minus 1 divided by n. Instead of n we write n minus 1. ln n minus 1 by n. Plus what is an? ln n by n plus 1. Okay. Now you simplify the terms. Okay. So ln 1 by 2 I can write as ln 1 minus ln 2. ln a by b. ln a minus ln b, right? ln a by b. So next ln a by b. So ln 2 minus ln 3. ln 2 minus ln 3. Okay. Next ln 3 by 4. That means ln 3 minus ln 4. Okay. Next, so plus this one up to so on plus ln n minus 1 ln n minus 1 minus ln n. Okay. So plus and the last one ln n minus ln n plus 1. That's it. Now look at the terms. Look at minus ln2 plus ln2 out. Minus ln3 plus ln3. Minus ln4 next plus ln4 will be there. That will be cancelled out. Look at plus ln minus ln. And this ln minus 1 minus ln minus 1 will be cancelled with the previous bracket. So first and last term will remain here. Okay. So therefore, what is the first term now? So therefore, first term is ln1 and last term is ln n plus 1. So it is also one of the example of telescoping series. So except first and last, all the terms are cancelling out with pairs. So this is second example of a telescoping series. This one ln n by n plus 1. So this is Sn now. Next one obviously limit n tends to infinity Sn value. Sn. So limit n tends to infinity. ln1 is 0 actually. It is 0 minus ln of n plus 1. What will get? 0 minus infinity. So this is minus infinity. So therefore what I can say now? So therefore sequence of nth partial of Sn is diverges because minus infinity is not finite number. Diverges. So once sequence of nth partial sum is converted, diverges. Therefore series an, which is series ln of n by n plus 1 plus 1 is also diverges. That's it. Look at it is not converges. That's why converse of the theorem is need not be true. Here nth term is going to 0, but series is not converging. Look at once again. Look at nth term is going to 0 here. Nth term is going to 0, but what is happening? The series is not converging. Here the series is not converging. but nth term is going to 0 here. So here nth term is going to 0. Okay, so therefore from now onwards, if you are having a convergent series, then I can say that limit n tends to an is 0 but not converse. Okay, that the theorem says. Next theorem, theorem number 3, the nth term test for divergence. Nth term test for divergence. See, remember all these theorem statements. So by using with these theorem statements, easily we can say the convergence status of a series. Okay, just you should make a grip on these theorems, nothing else. Okay, look at this theorem. I will give the proof for this. If limit n tends to is n is not equal to 0, so given that limit n tends to infinity, an is not equal to 0. This is given to us. Then we have to prove that. Then we have to prove that series an is not equal to 0 or fails to exist, or fails to exist, then we have to prove that series an diverges. Okay, so first use the given information. So the given information is limit n tends to an is not equal to 0. Okay, so based on this I need to prove that the series is diverges. So I want to prove in a contradiction way. Assume series an is converges. Actually I need to prove that series an is diverges, right? I want to prove in a contradiction method. What I am taking, assume series an is converges. Okay, so by using theorem number 2, look at theorem number 2. If series an is converges, so therefore by theorem number 2, just now we did theorem number 2, by theorem number 2, limit n tends to infinity, what is an value? 0. If you are having a convergent series, compulsory limit n tends to n value 0. But this is contradiction, right? Why this is contradiction? Because it is given that limit n tends to n value how much? Not equal to 0 or fails to exist. But I am getting n is equal to 0. This is contradiction. So therefore our assumption is wrong. So then what is correct? So therefore that is series an is converges is wrong. So therefore series an is diverges. That's it. Hence the proof. Again same, it is not if and only if statement. Look at, you find the limit value. If the limit value is not equal to 0 or does not exist, then directly your conclusion is series an is diverges. For example, if limit an is equal to 0, you cannot conclude that this is diverges or converges. Just now I told you, converse of the theorem number 2 is need not be true. So if limit n tends to an is equal to 0, we cannot say that the corresponding series an is converges. I can comment only if limit n tends to an is not equal to 0 or fails to exist, then only I can comment series is diverges. Let's have the similar problems depending on theorem number 3. Find the convergence status of these problems. You look at one by one. Look at first one. So limit n tends to infinity, an value. So limit n tends to infinity. Now what is an? N plus 1 by n. Look at the first problem. Okay. Now what is this? So this is limit n tends to infinity, 1 plus 1 by n, right? 1 plus 1 by n. Separate it. N by n plus 1 by n. So this is nothing but 1. This is not equal to 0, right? So therefore, what is the conclusion? So therefore, by theorem number 3, by theorem number 3, or simply write a theorem name, divergence test, right? Nth term divergence test. By theorem number 3, series 1 n plus 1 by n is diverges. That's it. Diverges. Understood? Since all the terms are positive, therefore diverges to infinity. Therefore, the sum of all the terms are infinity. Diverges. Because terms are positive, sum of positive terms is positive only. So therefore, I should get infinity. That's why it is diverges. Because it is condition is satisfying. Limit n tends to infinity, a value is not equal to 0. Okay. Similarly, second one, yeah, limit n tends to infinity, an. So limit n tends to infinity. What is an now? N upon 3 plus 2n. Let us take n common in the numerator, n common in the denominator. What will get? 1 by 2 will get, right? Check once, which is again not equal to 0. So therefore, again by using same theorem number 3, by theorem number 3, write the theorem statement in exam. By theorem number 3, series n by 3 plus 2n is diverges. Diverges to what number? Can you guess? More information? Give me more information. At what number the series diverges to plus infinity or minus infinity? Plus infinity only. Why? Because terms are positive. So sum of positive terms is again positive only. That's why diverges to infinity. That is extra information. Next one, third one. So again same, limit n tends to infinity, an value. So limit n tends to infinity, minus 1 whole to the power of n. Again same story, you will be having two limits. If n is even, you will get plus 1. If n is odd, you will get minus 1. Two limits you are having. So therefore fails to exist. Again same, again conclusion. Again by theorem number 3, what I can say? Therefore by theorem number 3, what I can say? Series minus 1 whole to the power of n is diverges. I proved this one by using nth partial sum concept. Look at once. And I am proving by using theorem number 3 also. Look at, yeah, various techniques I am applying for the converging status of the series. So the only thing is you should have a complete grip on the theorems and statements. So once you are having a complete grip, then you can play with the problems. Otherwise, problems will play with you. Decide yourself. Okay? Yeah, next one. Fourth one. Series an, which is series n square. Okay? Now, so limit n tends to infinity an, which is limit n tends to infinity n square. What is this? Infinity. This is not equals to 1, right? So therefore we can conclude. So therefore, same story again by theorem number 3, or divergence, nth term divergence test, we can say that series n square is diverges. Or you no need to apply theorem number 3, directly you observe the terms. What are the terms now here? 1 square plus 2 square plus 3 square plus up to so on. Look at 1 square plus 2 square, 5, 5 plus 9, 14 plus up to so on. You are adding all the numbers. So you are getting infinity, right? So this is infinity. Therefore it is diverges without applying any theorem statement. You can conclude like this also. Okay. And fifth one, 1 over n. Fifth one, limit n tends to infinity an. So which is limit n tends to infinity 1 upon n. What is this? I am getting 0. What is the conclusion? If, look at, if limit n tends to infinity, an is not equal to 0 or fails to exist or does not exist, whatever, or fails to exist, then only I can comment. Okay, then only theorem number 3 can be applied. But here it is not So therefore, what is the comment here? So therefore, by theorem number 3, we cannot conclude. It can be converge, it can be diverge. We cannot say now. Don't say it is converges or diverges, because condition is satisfying, it is diverges. Condition not satisfying means not converges. Don't say like that. Okay, we cannot comment. Therefore, by theorem number 3, we cannot conclude. So then what is the convergence status of this? So by applying other techniques, we need to find the convergence status of series 1 by n, and that I will do in the coming class. Okay, so this you will think of this, what is the convergence status of this. But by using theorem number 3, I cannot conclude. Then use other techniques for the convergence status of series 1 by n. Okay, next one. Theorem number 4, if series an converging to a and series bn converging to b, or both are converging series, okay, then first one, sum rule, series an plus bn is equal to a plus b, and difference rule, series an minus series bn is equal to a minus b, and constant multiple rule, k into an, series k into an, k will comes out, and series an will be a, because series an converging to a. So by using theorem number 4, let us do this problem. So problem number 11. Okay, so the series n is running from 1 to infinity, 3 raised n minus 1 minus 1 upon 6 raised n minus 1. So this I am writing separately. Series n is running from 1 to infinity. First 3 raised n minus 1 divided by 6 raised n minus 1. Okay, minus series n is running from 1 to infinity. Okay, 1 upon 6 raised n minus 1. This is by using difference rule. Okay, difference rule. By difference rule, we can apply limit separately for series n minus series bn like this. And this can be simplified as, so 3 by 6 whole to the power of n minus 1 I can write. Okay, 3 power n minus 1, 6 power n minus 1, overall 3 by 6 whole power n minus 1. So minus series n is running from 1 to infinity, 1 upon 6. Okay, 1 upon 6 whole to the power of n minus 1. Okay, now this is 3 by 6 means what it is? 1 by 2. Okay, so right here, so series n is running from 1 to infinity, 1 by 2 whole to the power of n minus 1, minus series n is running from 1 to infinity, 1 by 6 whole to the power of n minus 1. Look at both are geometric series, because r is lying in the interval minus 1 to plus 1, and 1 by 6 also lying in the interval minus 1 to plus 1. So therefore, this series converges to a by 1 minus r. Let me write the terms first. So what is the first term? 1 plus 1 by 2 plus 1 by 2 square plus to so on. This is the expansion of first series, minus expansion of second series, 1 plus 1 by 6 plus 1 by 6 square plus 1 by 6 cube plus up to so on. Right? Since it is geometric series, and here a is equals to 1, here a is equal to 1, and r is equal to 1 by 2, and in this a is equal to 1, and what is r is equal to 1 by 6. So clearly r is lying in the interval minus 1 to plus 1, therefore this series converges. And here also, since r is lying in the interval minus 1 to plus 1, therefore this series also converges. So both the series are converges, and it is converges to which number? Let me write here. So therefore first series is converges to a by 1 minus r. So a means 1 by 1 minus r, 1 minus half, plus second series is, sorry, minus, right? Minus, and second series is converges to a by 1 minus r. So a means 1 minus 1 upon 6. So overall it is 1 by 2. So 2 minus 5 by 6, right? 5 by 6 means 6 by 5. So overall 5 2s are 10. 10 minus 6 by 5. that means 4 by 5. So therefore the given series, sum of the given series is which is 4 by 5. It is converges to 4 by 5. Okay. Next one last one note. With this I will stop. Adding or deleting terms. Addition and deletion of a finite number of terms from a series will not alter its convergence or divergence. Alter means what? Changing. It will not change its convergence or divergence. For example, series An is converges. Series An means what? A1 plus A2. See, for example, I am taking series An. So series An, n is running from 1 to infinity. Okay, which is nothing but A1 plus A2. Okay, plus A3, right? Plus up to so on. And assume this is converges to some number L. So a finite number of terms I'm adding. That means, for example, let's say b1 and b2 are finite numbers. Are finite numbers. Finite numbers. So therefore, what can you say about this one? A1 plus A2 plus A3 plus up to so on plus b1 plus b2. I'm adding these two terms extra. Can you guess what is the limit value? L plus b1 plus b2, right? Both sides are adding b1 plus b2. Since b1 and b2 are finite, so L plus b1 plus b2 is also finite. Therefore, let's say this is some L1. So again, this series is converges. Look at how many terms are there? Infinite terms are there again, because plus up to so on I have written. That's what the note here. Addition and deletion of a finite number of terms from a series will not alter and means will not change its convergence or divergence. If the original series is converges, then after adding two finite terms, then also it is converges. Or deleting, for example, a1 I am deleting from this. Again it is converges. So you write minus a1 this side and minus a1 this side. L minus a1 will get. Again L minus a1 is finite number. For example, if it is diverges, let's say a1 plus a2 plus a3 up to so on, all these diverges. That means plus infinity. Let's say it is plus infinity. That means this series is diverges. Then if I am adding two finite terms b1 and b2, then this is also infinity only, right? Then this is also diverges. So will not alter its convergence or divergence. That's what the note. However, the addition or deletion of a finite number of terms from a convergent series will change its sum. Sum will change. Look at if previous series is converged to L. Now the original series means what? After adding these two terms B1 and B2, now I am getting sum is L1. So previous sum is L. Now this sum is L1. Sum is changing. Definitely sum will change because we're adding two terms. That's what here. So that is about this note. Okay, and with this I will stop.